Okay, so the main focus of this video is going to be exponents, and especially towers of exponents. So let's say we have something like 10 to the power of 10 to the power of 10 to the power of 10. There's an order of operations that goes along with this. So in high school you learn about things like bed mass. Well, this also has an order of operations, and it's top down. So the first thing we do here is we start at the top with 10 to the power of 10, which is equal to 10 billion. Then we take 10 to the power of that, and then 10 to the power of that. Because if we start at the bottom and work our way up, we're going to get a completely different answer, and we don't want that. We want consistency. So that's very, very important that whenever you have a tower, you work from the top down. Now, another important function that we're going to need when evaluating exponents is something called a logarithm. And it basically takes the form, it's denoted as log. It has a subscript called a base, and then an input to the function. And just that'll equal whatever the thing that we're trying to figure out is. Now, basically what this equation is asking is a to the power of what is equal to b. So let's do an example. Let's say we have something like log base 10 of 1,000. What is that? Well, basically this is asking 10 to the power of what is equal to 1,000. And we all know the answer. It's 10 to the power of 3. So the answer to this is 3. Another example, using something different than tens. Let's say we have 2 to the power of something. So that one, in this case, would be log base 2 of, let's say, 16 is equal to what? Well, it's asking 2 to the power of what is equal to 16. The answer is 4. So how does this help us? What does this do for us? It basically allows us a way to transfer, change the base of two exponents. So let's say we have something like 2 to the power of 50. And we want to figure out that is 10 to the power of what? So in order to solve this, let's make a more generalized form of the equation. So let's say we have 2 to the power of x, the thing that we're plugging in, and we want to figure out the y over here. So 10 to the power of y, and our job now is to isolate this y. How do we do that? Well, the way is with logarithms. Basically, we can take log base 10 of both the sides here, and we can make this 10 go away, and we're left with just y. And to see why that's the case, let's just take an example. Log base 10 of 10 to the y. What is that? What's it asking? It's basically asking 10 to the power of what is equal to 10 to the power of y, and this is trivial. Of course it equals y, so this is equal to y. So in this case, the function log base 10 gets rid of the 10 here. So we're going to utilize that now. Let's take log base 10 of both sides of the equation. So log base 10 of 2 to the x is equal to log base 10 of 10 to the y. This part here is going to go away. We'll be left with just y on the right-hand side. And what happens on the left-hand side here? Well, we're going to use a rule of logs here to rearrange this a little bit. And the rule is log base a of, let's say, b to the c is going to equal c times log base a of b. So basically, you just take this exponent up here and you drag it out front. And that's something that's that we can do. So let's do that. We rearrange this and we pull this exponent out. And we have x times log base 10 of 2 is equal to y. So now we have everything we need to solve this equation up here. So let's go back to this equation. 2 to the power of 50 is equal to 10 to the power of what? Plug in our numbers. Our x here is going to be 50. So we'll take 50 times log base 10 of 2. So you'll need to plug this into your calculator, and you'll get roughly 0.301. This is going to equal around 15.05. So in our equation, we can write this as 2 to the power of 50 is equal to 10 to the power of 15.05. So we can change the base of this exponent using logarithms. Now I'm going to do another example here, this time involving a tower of exponents, basically. So let's say we have 2 to the power of 10 to the power of 10, and we want to figure out what 10 to the power of 10 to the power of something is. So we want to figure out this question mark here. Now, this might seem a little strange why I'm going through all this stuff about logarithms. It seems a little strange considering this is videos about extremely large numbers, but it'll become clear pretty soon. I want to show you how this base changes as the towers of exponents get larger and larger, and it's a very interesting property. So just bear with me. To figure out this equation here, we're going to do the exact same thing as before. We're going to make a generalized form of the equation. So instead of having a 10 up here, we're going to have an x, so we can plug in anything we want. So it's 2 to the power of 10 to the power of x is equal to 10 to the power of 10 to the power of y. So the exact same thing, we're going to take log base 10 of both sides to get rid of this 10 here. So we're going to end up with log base 10 of 2 to the 10 to the x is equal to, and I'll just skip a step here and just get rid of this 10 here, because we know that if I take log base 10 of this 10 just goes away. So I'll just be left with this part here. So that equals 10 to the power of y. Well, now what can we do? Basically, we can do the exact same operation, because we still have a 10 here that we need to get rid of to isolate this y. So let's do that. We'll do the exact same thing again. We'll take log base 10 of both sides. So we end up with, or actually, you know what? First of all, before we do that, we're going to rearrange this a little bit too, using our rule. Because remember before, we know that we can pull this exponent out front. So first, before we do anything, we're going to do that. So sorry, I skipped a little step there. 10 to the power of x times log base 10 of 2 is equal to 10 to the y. Okay, so now we can take log base 10 of both sides again. So let's do that. Log base 10 of 10 to the x times log base 10 of 2 is equal to y, because the log base 10 just got rid of this 10 here and we're left with y. Now we're going to exploit another rule of logarithms, which is basically log of a of b times c is equal to log of a of b plus log of a of c. So we can use that here because we have two things multiplied together. So we can rewrite this as log base 10 of 10 to the x plus log base 10 of log base 10 of 2. Okay. And that's going to equal y, basically. And again, we can pull this x out front, so we end up getting x times log base 10 of 10, which will go away. So we're actually just end up with x on this side, x plus log base 10 of log base 10 of 2 is equal to y. So let's just get rid of this part here because we know it cancels out. And that's the final form of the equation. I'll move this x over where it's supposed to be because it looks ridiculous. Okay, x plus log base 10 of log base 10 of 2. Okay, so this right here is going to be a constant. This will never change. So we can just figure out the value of this. We know log base 10 of 2 is 0.301. When we plug that into a calculator, log base 10 of 0.301, we get negative 0.214. So basically, whatever we have for x, we just minus 0.5214, and we get the final answer for y. So what was our original equation here? It was 2 to the power of 10 to the power of 10 is equal to 10 to the power of 10 to the power of what? Well, this is our x here, and 10 minus 0.52 is going to be something like, what is it? 9.48, yeah. So now we have an interesting property here. We noticed that when we first started here, changing the base from 2 to 10 changed this number from 50 to 15.05. So that was quite a significant change. But down here, when we had a tower of exponentials, when this 2 was down the tower a couple instead of right underneath it, when there's a tower of 3, this number only changed from a 10 to a 9.48. So this exponent had to change a lot less to change this base to a 10. And what you end up finding out basically is the longer the tower is, so let's say we had like 2 to the power of 10 to the power of 10 to the power of 10. If you want to change this base down here to a 10, this number up here only changes by a millionth or something, a millionth of the value. So this ends up being like 9.9999997, I think. So this is a very, very interesting properties of exponentials, because you can pretty much change the base here into a 10 with virtually no consequence to the number, because for all intents and purposes, 10 is the same as 9.9999997. So when we have towers of exponentials where the base is a certain number down the tower, let's say around 3, we can do this. Is about 10 to the power of 10 to the power of 10 to the power of 10. And this is a very counterintuitive property, because we wouldn't think this. We wouldn't think a number that is basically, when you come down to it, just multiplying a bunch of 2's together. That's what the definition of this would be. You think this would be vastly, vastly smaller than a number that just that multiplies a bunch of 10's together. But in fact, it's not. You can approximate these two, and it's actually a very good approximation. And the further you go with the towers, the better of an approximation it is. So if I had something like 2 to the power of 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 2, and I just add like 3 more 10's up here, I can change all these 2's into 10's with virtually no consequence. This is basically be a very similar number, which is a very, very strange property. So that's the reason why I wanted to go through logarithms and stuff, to really show you the strange properties that we get when we start dealing with towers of exponentials and whatnot. And I think I'm going to leave it at that for now. And the next video we'll start getting into some actual large number things.